Good morning. So, we have one more day to go. This is getting closer. But today, in the morning, I am going to talk about the first topic is physical properties and characterization. So, it's in general it will cover magnetic phase, the ferroelectric phase, and most of the measurement techniques for magnetoelectric coupling we have looked at it already. So, I will just breeze through it, but I will mainly focus only on specific properties of ferromagnets and ferroelectrics. So, I am pretty sure most of you are familiar with ferromagnetic order, where there is spontaneous magnetization because of parallel alignment of atomic moments. And so, overall, below the Curie temperature, there is a finite magnetization. Above the Curie temperature, because of the thermal energy, there is random ordering of the moments. So, the spontaneous moment goes to 0. So, ferromagnet is very similar to ferromagnetism, but there are two kinds of magnetic moments. They are aligned antiparallel to each other, but they are not equal. So, that would mean that there is a net magnetic moment. So, the system behaves very much like a ferromagnet. So, the ferromagnetic ordering, those materials are generally called ferrites. So, ferrite would mean the ordering is ferromagnetic. But people kind of misuse the term because they call it bismuth ferrite, but it is not a ferrite. It is antiferromagnetic or very weakly ferromagnetic. So, you have to be careful when you call something a ferrite. Ferrite implies ferromagnetic ordering. Then you are also familiar with antiferromagnets, where there are two moments equal and opposite. So, the net moment is 0, and there are many materials that are antiferromagnetic. Manganese oxide, MnO, nickel oxide, cobalt oxide, iron oxide, they are all antiferromagnetic. Then the other kind is canted antiferromagnet. So, the arrangement is antiferromagnetic, but there is a net angle between the two moments, that is canted structure. There is also helical spin ordering. If you imagine a helix, the spins, the neighboring spins, they are making a certain angle like a cone. So, the helical spin ordering is very much like what is shown in this figure. So, the ferromagnetism, it's spontaneous magnetization, and it's arises because of ordered spin state in a magnetic material in the absence of any external field. So, it happens below a certain critical temperature, which we know it is Curie temperature. So, when heated above the Curie temperature, it becomes paramagnetic. So, the magnetic moments are strongly coupled through exchange interaction. So, anything that happens in one spin, it will be transmitted to the neighboring spin. So, it is collective excitation. The whole system behaves like what we call spin waves or magnons. These are bosons. They have very small energy on the order of milli-electron volt. So, the temperature dependence of the magnetization is given by this equation here. That is true only when you are far away from the Curie temperature. So, there is a 3^2 exponent in the way the magnetization decreases with temperature. But the one at the top, that equation fails when you are close to the Curie temperature, and very close to the Curie temperature, the magnetization will vary like what's shown here. Beta is called the critical exponent. It ranges, it's less than 1 certainly, anywhere between 0.3 to 0.5 depending on the material. But if you want to find the Curie temperature for a ferromagnet, strictly speaking, it should be done under 0 external field. If you apply an external magnetic field, there will be a spread in the Curie temperature. That's what is shown here. Now, these curves are shown for a series of fields 1 kg, 6 and 12, and as you increase the field, there is some error in the Curie temperature that is very evident from the way the magnetization varies with temperature for these 3 cases. So, how do you measure the magnetization? There are many ways to do that, and I will just quickly go through some of them. Vibrating sample magnetometer is commonly used, and this is what I have in my lab, the Faraday susceptibility balance, and there is also what is called an AC gradient magnetometer, and this figure shows a typical VSM, and the one on the right is the power supply and all the electronics for the system, and what is shown on the left is an electromagnet that will apply a magnetic field to measure the magnetization as a function of the static magnetic field. So, what you see here is a sample holder that keeps the sample between the 2 pole pieces, and then this is the vibrating unit, and the sample is attached at the bottom of this. These 4 coils are just copper winding placed very close to the sample. It can be mounted on the pole pieces or away from it, it does not matter. So, when you vibrate the sample has a magnetization and there is a magnetic flux. So, the flux will change as a function of time. So, from the Faraday law, you can estimate that there is an induced voltage in these 4 pickup coils, and that is given by the time derivative of the magnetic flux associated with the sample. So, you can use a standard such as nickel and do some calibration, and then for unknown sample just put it in, and then you can find the magnetization versus static field, and this can be done as a function of temperature or anything else that you want. And the Faraday magnetometer, it is as sensitive or even better than a VSM. What's here is an electromagnet with a tapered pole piece. The purpose of this is the field configuration produced by this magnet in such a way that there is a gradient in the magnetic field in the vertical direction. So, if there is a gradient, then there is a force on the sample. So, this force will pull the sample down, and there is a control electronics with a photo detector. So, when the sample moves down because of this magnetic force, it allows more light to go into the system. There is a photosensitive detection that will sense the deflection of the sample, then it will send a signal to correct for that. So, ultimately what you get is the unit produces an output which is proportional to this force, and the expression for the force is given here. Chi is a susceptibility, H is the field produced by this magnet, and dH dz is the field gradient along the z axis. So, once again the system is calibrated with a known sample. We use manganese fluoride, which is a paramagnetic material. So, once you calibrate the system, any unknown sample, then you can mount it and do the measurement. Now, there is no need to shape this pole piece for the permanent, for the electromagnet to produce this gradient. Instead, in our system, there are coils which are called Lewis gradient coils. It is a solenoid where the number of turns per centimeter is changed. So, when you do that, there is a change in the magnetic field produced by the coils in the vertical direction that will produce the force. So, it is rather easy to do than shaping the pole pieces into a parabolic shape. That is rather difficult to do unless you have special machining to do to take care of that. Now, the alternating gradient magnetometer is similar to the Faraday balance. The Faraday balance, there is a gradient acting on the sample. That is a DC gradient. It is a gradient in the DC or permanent magnetic field. Whereas, in the AC gradient, there is a coil that would produce a gradient felt by the sample, which would change with time. So, this one would make it easy for detection of the magnetic moment, and so it is little bit more sensitive than the Faraday balance. But other than that, the only difference between the two is one is DC magnetic field gradient, the other is AC. So, all three are available from commercial system manufacturers, and most expensive one is the VSM, because it has the capability for low temperature measurements, and also you can have the sample parallel to the field or perpendicular to it. So, you can get the hysteresis loop in plane or out of plane. So, that will allow you to determine the anisotropy field and few other things. And the Faraday balance, you do not have the freedom to align the sample, because the sample always aligns along the EC direction. So, if it is the in plane is, if that is the EC direction, it will always align that way, and there is no way to turn the sample and to make it perpendicular, because it is a freely suspended sample on a thread or a wire, and you do not have the freedom to do it. The AC gradient is little bit better. You can reorient the sample the way you want if necessary. Right. Then the magnetic domains, in a ferromagnet, the sample splits into many regions in which the magnetic moment is aligned parallel to each other. These are called domains. Why would there be any domain formation? What is the reason for it? Okay. So, all the way left, this is a ferromagnet where the moment is all in one direction. So, if you look at the field lines will travel through the air surrounding the material, and that is not the state of minimum energy. Instead, the middle one shows this splitting into two different orientation, up and down. So, these are two domains, these are 180-degree domains, and this has little bit less magnetostatic energy compared to the previous one. But the third one is even much less magnetostatic energy. These are 90-degree domains. As you see here, the field lines are confined to the interior of the material, that is the minimum energy state. All systems in the universe, they will try to be in a state of minimum energy. You pick up something and let it drops because it has a potential energy. So, at the ground level it has zero potential. So, that is what really happens. Any system, no matter what, it will always try to be in a state of minimum energy, and the domain formation is just because of that. And you can image the domains in either single crystal or polycrystalline material. There are many ways to do it. What you see here is the domain imaging by Kerr effect. Kerr effect is you shine light onto the sample surface, then you get the reflected light through a polarizer and an analyzer, depending on the grain orientation of the magnetization. So, there will be a small change in the polarization angle, and when you use the detection, the different grains will show up as a change in the contrast. So, these are grains of different orientation on the surface of some, I do not know what sample is this. So, that is how you do the grain imaging using magnetooptic Kerr effect. There are other ways to do it, and people used to do this bitter technique. What you do is you take Fe3O4, which is a ferrite, and just dissolve some of it in alcohol. Then you polish the sample pretty well, and then disperse this magnetic particle on top of it, and they will orient in the direction, because if there are domains, there is a domain wall separating two domains. So, there is a field gradient, because the magnetization, they are oriented in different direction in two neighboring domains. So, at the interface there is a gradient. So, all the magnetic particles will be attracted toward where the gradient is maximum. So, it will accumulate right at the domain boundary, and this is how you visualize the domains using the bitter technique. But there are much better ones now. The Faraday rotation imaging is similar to Kerr effect, but you look at the domains in the transmitted light. You allow light to go through your thin film sample, because the film has to be transparent for it to work. Then you look at the light transmitted with a polarizer. So, depending on the grain orientation, there will be a change in the angle of polarization, and that would show up as domain structure. And these are what are called 180 degree domains, and the sample has an anisotropy perpendicular to the plane. So, what you see as bright one is domains with magnetization up, the dark ones are domains with magnetization down. So, these are 180 degree domains that we saw earlier, and these are seen in the Faraday rotation imaging. And when this is usually Utrimer and Garnett, I am pretty sure. And if you have a small static magnetic field, you can easily visualize the change in the domain configuration. It's 4 Oersted, that is a very small field versus 0. Okay. And this one is magnetic force microscopy. You can image the domain structure in the MFM amplitude or phase image, and it's a traditional atomic force microscopy technique, but the probe is sensitive to magnetization. That is what shows up this domain structure. Right. You are familiar with hysteresis. What really happens is, for example, if you load your sample in a vibrating sample magnetometer, and you start increasing the static magnetic field. So, initially when there is no field, the sample has domains with magnetic orientation in different direction. So, the net moment as a whole is 0. That is the reason if you bring two pieces of iron together, nothing really happens, because they are all split into domains. The net moment is 0 in the two pieces. Unless you apply a magnetic field, you would not realize that it is rather magnetic. So, when you apply a magnetic field, there are two things that happen. The domains in the direction of the magnetic field will grow at the expense of domains with opposite orientation. And also there is domain rotation. So, now the whole domain magnetization will rotate and will try to align in the field direction. So, it is domain wall motion where the domains grow and the domain rotation. These are the two mechanisms, and that is what really happens as you keep increasing the field. The magnetization increases until you reach saturation where all the domains are oriented in a particular direction, which is the direction of the field that is applied to it. Then you go back and the magnetization will decrease, but when you hit 0 field, it does not quite go to 0, because some of the domains are left with partial orientation parallel to each other. So, there is a non-zero magnetization when you go to 0 external field, and that is what is called the remnant magnetization. So, there is saturation magnetization when all the domains are aligned parallel, and then when you go back to 0 field, the leftover magnetic moment is called remnant magnetization. Then you reverse the field until you hit the coercive field, when the domains are reoriented in such a way that the net magnetization is 0, then you keep going on the other direction, then it saturates, then you come back up. This process repeats. So, this is true for all ferromagnets, but it may have different characteristics. A permanent magnet like barium ferrite or strontium ferrite will have a very large remnant magnetization, whereas nickel ferrite may not have that high a remnant magnetization, and it will drop to close to 0. Now, these are two different cases. One is a soft magnetic material, it is a soft ferromagnet, and the coercive force or the coercive field or the field where you can make the magnetization to go to 0. That means when you want the remnant field to vanish, so the coercive force is very small, and that is the characteristic for soft ferromagnets, and it is true for iron, nickel, cobalt. Cobalt is a little bit hard, but iron, nickel, permandur, these are all soft. Nickel ferrite is soft magnetic material, and the hysteresis will look like this with a small Hc value. But barium ferrite, strontium ferrite, alnico, samarium cobalt alloy, they are all hard ferromagnetic materials, and they will have a very large coercive field. So, for a permanent magnet, you would like to have this kind of hysteresis loop, where the leftover magnetism under 0 external field is large enough so that it will behave like a magnet without having you to apply an external field. It is already magnetized, it keeps some of the magnetization, and that is what you realize with a permanent magnet. So, the permeability is essentially the slope of this M versus H at low field. So, the initial permeability is the magnetic induction over H. The what is shown here is B versus H. B is equal to H plus 4 pi m, and so it is called magnetic induction, and mu m is at the knee of the magnetization curve. Okay. So, the maximum permeability is where this maximum in slope. So, that occurs somewhere in the middle point. So, the initial permeability is a key parameter. So, it tells you that whether the material has high affinity for an external magnetic field. When the permeability is very high, the field lines due to the external field, they are likely to go through the material rather than in air. So, you want high permeability materials for use in certain applications. So, what is magnetocrystalline anisotropy? Now, we just saw there are domains in a ferromagnet. So, when you apply an external magnetic field, there is rotation of the domains as well as there is also the domain wall motion. These two mechanisms will involve some energy. So, when the magnetic field is applied in different direction, it takes more for you to do the magnetization in a particular direction than some directions are easy. So, the easy directions behave as if there is an internal magnetic field present in the sample. That internal magnetic field is called magnetocrystalline anisotropy field. Why does it happen? Because you know that the magnetic moment essentially arises from two sources. One is the spin of the electron, the other is the motion of the electron in a circular path around the nucleus. So, that is orbital motion, and there is spin orbit coupling, because when the electron moves, there is interaction between the electron and the crystal lattice. The crystal lattice will produce an electric field. For example, in nickel ferrite you have oxygen all around, right? It is negatively charged. So, it will produce an electric field. So, the electrons, they have a coupling to the lattice, which is called spin lattice coupling and spin orbit coupling, and those two sources will give rise to this inherent magnetic field, which will define an easy direction for the magnetization. So, it is as if there is an internal magnetic field present in the sample. That is magnetocrystalline anisotropy field. It can be small or large depending on the material. For example, some of the spinel ferrites like nickel ferrite, it is not very high, it is about 500 Oersted. But in barium ferrite or strontium ferrite, these are hexagonal structure and it can vary from 17 to 18 kilo Oersted. And if I substitute aluminum in barium ferrite, you can hit values as high as 40 kilo Oersted. So, barium and strontium ferrites, they are uniaxial, the field is along the C direction, but some of the hexagonal ferrites, they have easy plane. So, it does not matter, this is the C plane of the sample, and any direction within the plane is easy direction. Okay? So, there is no preference. So, there are easy direction and easy plane anisotropy, and that is the source of magnetocrystalline anisotropy. And you have in the case of permanent magnets, the uniaxial anisotropy field that leads to the permanent magnetization, a large permanent magnetization that will make it like in the refrigerator you have the magnet. These are all made of barium or strontium ferrite dispersed in a flexible medium such as rubber. You have the lining with barium ferrite, and it will attract, and then the fridge door will close properly for you to keep everything cold inside. And magnetostriction is also related to the motion of the domains under a magnetic field. So, as we know, when you apply an external magnetic field, these domains will either rotate or move toward grow with maximum volume toward the field direction. So, these would involve a shape change in the bulk of the material. So, some mechanical strain, that strain is what we call magnetostriction, and the strain will increase as you increase the external magnetic field, and ultimately it will reach its saturation value. This is the magnetostriction versus static magnetic field for iron and nickel, It's the iron at low field it is positive, it goes through 0 and then it's negative. It's nickel, it's negative all the way, but ultimately they all reach saturation. Okay. So, cobalt it has positive magnetostriction, nickel has negative, permanganate has positive, and lead glass that we saw earlier it has positive magnetostriction. So, there is nothing unique about whether it can be positive or negative, it could be either one depending on the nature of the material, but the driving mechanism is the rotation and expansion of the domain in the ferromagnet under an external magnetic field. So, you can measure the magnetostriction using several different techniques. You can use optical interferometry, strain gauges, that is what we use, and also you can use piezoelectric transducers or some resonant techniques to measure these. For our interest, most of the ferromagnetic materials, you can measure the magnetostriction with a strain gauge and a strain indicator. This is the easiest method instead of using something fancy like optical interferometry. Okay. And we know about this, I showed this earlier, this is the strain gauge, it forms a Wheatstone bridge. So, the bridge output goes to the strain indicator, and whenever there is strain, the resistance of this arm will change. So, leading to a condition away from balance. The strain indicator will correct for that and will produce an output which will show the strain in parts per million. Okay. So, you can directly read what the strain is, and it can be measured parallel to the magnetic field or perpendicular to it, it does not matter. You put the strain gauge on the sample. For parallel for magnetostriction, you apply the field along the strain gauge direction. For perpendicular, you just apply perpendicularity, that is all. You can also do lambda 1 1, 1 2 and 1 3. Okay. All right, let us go on to the next one that we are interested in. The other phase that we use in most of the composites, it is either ferroelectric or piezoelectric. In a ferroelectric, similar to a ferromagnet, in the ferromagnet there is spontaneous magnetization. In a ferroelectric, you have spontaneous electric polarization, and that can only be reversed if you apply an electric field, similar to the case of a ferromagnet, where you cannot reverse the magnetization direction unless you apply an external magnetic field, and it takes energy to either reverse the polarization or realign the ferroelectric domains in the ferroelectric. And piezoelectrics, they are not ferroelectrics. Most all materials are piezoelectric in the sense that if you apply an external electric field, there will be mechanical deformation, like such as quartz or aluminum nitride. These are not ferroelectrics, but they are all piezoelectrics, because there is always a change in the charge configuration that will lead to a dipole moment under only external electric field. And this is the traditional hysteresis loop associated with a ferroelectric. D is the displacement, and it is sum of 4 pi E plus the polarization. It is very similar to what you have for ferromagnets, B versus H. This is D versus E. So, you can polarize the ferroelectric, it is okay, but there is always their resistivity is not infinite, it is finite. So, you have accumulation of charge, positive charge on one end, negative charge on the other end when all the dipoles are oriented in a particular direction. And there is always a force of attraction between positive and negative charges. So, there is always a current, it is a leakage current. So, ultimately if you do not do anything, if you remove the external electric field, the leakage current will cancel out all the charges, you will end up with zero polarization. Okay. So, some of the examples for ferroelectrics are PZT, barium titanate, and PM and PT. These are called relaxer ferroelectrics, and barium titanate and PZT are traditional ferroelectrics. So, the transition from ferroelectric to paraelectric state is very sharp in PZT and barium titanate, whereas in PM and PT, if you look at the polarization versus electric field as a function of temperature, it is rather very shallow. So, it occurs over a wide temperature range and it is not very sharp. So, that is the signature for relaxer ferroelectrics. And this one shows traditional ferroelectrics such as barium titanate or PZT for temperatures above the ferroelectric Curie temperature. The structure is rather cubic, and the titanium or zirconium, they are all placed right at the center of this octahedron. So, the center of positive and negative charges, they overlap. The negative charge here is oxygen, the positive charge is either titanium or zirconium. So, when there is no separation between the center of positive and negative charges, the polarization is 0. But once you go below the Curie temperature, there is a slight displacement of the central ion, and so the center of positive and negative charges do not overlap any longer. So, there is a net accumulation of positive and negative charges separated by a small distance. So, there is net polarization, and this small polarization is the one that is responsible for the spontaneous polarization and the ferroelectric order. This is true for barium titanate as well. And these are typical polarization versus electric field for PZT at a series of increasing temperatures, and this one is the saturation polarization, and what you see here is the remnant polarization, and that keeps decreasing as you increase the temperature, and it will just vanish when you hit the ferroelectric Curie temperature. And this is the strain or D33 versus the electric field, once again for I believe these 975, maybe these are all the centering temperature when they made these PCT. So, when you make PCT, you have to be extremely careful, because lead has a tendency to evaporate and escape from PCT. So, in order to avoid any loss of lead that you need in the PCT, you always disperse some lead around it. So, that will compensate for any loss, and then you can get stoichiometric PCT if you make it. But we always buy PCT from vendors. It is not that expensive. You get them pre-poled with silver electrodes already deposited on PCT. They use silver paint to make those electrodes on top and bottom. So, we buy the platelets already pre-poured, and they are good enough. You can quickly make a composite and do whatever you want. So, there are depending on what exactly you want, you can substitute different ions into PCT and make either soft PCT or hard PCT. Soft PCTs are defined by a very high dielectric constant, a high D33 and rather small Curie temperature, whereas hard PCTs have much lower dielectric constant and smaller D33, but they have higher Curie temperature. Depending on the application, you may use either soft or hard PCTs. These are the ones the people, the companies made for applications in Navy. They use underwater transducers and other communication devices, and most of them use different types of PCTs depending on what exactly the application is. So, in our case we use soft PCTs because you want high D33 to achieve a large magnetoelectric response. So, we stay away from hard PCTs, and soft ones are the ones that we use. And barium titanate, it's similar to what I just talked about on PCT. So, the structure is cubic above Curie temperature. Below Curie temperature, it has a distorted structure. Barium ions are displaced from the center, leading to a polarization. P versus E will look like this. It's similar to what you have for PCT. And the strain is always either positive or negative. It doesn't switch sign when you reverse the electric field. So, these are electrorestrictive, and that is what you have for barium titanate, and PM and PT also the same way. These are relaxer ferroelectrics, and they have very high electrorestriction. D33 may be on the order of several thousand. For PCT, it's anywhere from 400 to 700 for the soft ones. Barium titanate is even smaller, whereas with PM and PT, you can get D33 as high as 2 to 3,000 in PM and PT and PC and PT. And the mechanism for the ferroelectricity is rather not completely understood, and these are relaxer ferroelectrics, and they are characterized by a slow change from ferroelectric to paraelectric state. So, it is spread over, the transition is spread over a large temperature range. That is not the case for PCT or barium titanate. And there are series of relaxer ferroelectrics, PMN, PT, PLZT, and PZN, PT, and several combinations. And so, you can differentiate all of them from the polarization versus electric field. This is just a piezoelectric, and that is P versus E is linear. So, when you go to a ferroelectric, so that is shown in B, where this is the characteristic that you see for PCT or barium titanate, and where there is saturation of the polarization, then you go back to 0 electric field, there is remnant polarization. The third one is what is called antiferroelectric. So, the moments are the polarization vectors are antiparallel to each other, and you do not have to worry much about it. We do not come across this. Lead titanate is antiferroelectric, for example. And finally, for relaxer ferroelectric, it is characterized by a thin P versus E, whereas this one is spread out, and the remnant polarization is rather small compared to traditional ferroelectrics. This is PM and PT, and so depending on the amount of lead titanate in PMN, it has very different characteristics, and these are shown here 28% PT and 37% PT. As you see here, we use most of our, in our systems, we use PT of 36 or 38, it has a much higher D33 among all the compositions available for payment PT. So, how do you measure? We have a ferroelectric tester made by a company called Radiant Technologies, and it has a holder, that is what is shown underneath. You can get P versus E, and also you can measure D33 versus E and so on. The middle one is a quick and dirty way of measuring D33. It is a simple setup. There is an external sample holder, or the one we use, it is an older model. The sample goes on top with a mechanical vibrator. It will vibrate on the sample surface, and then that will produce a voltage. The unit measures that voltage, and it is converted to D33 in the unit of picometers per volts. And also you can measure, with the traditional LCR meter, the capacitance across PCT. So, that way you can measure what the dielectric constant is. And these we have already seen in many of the earlier talks. So, measuring the magnetoelectric effects, we had demos in the tutorials on all these things. So, right. So, I will wrap up this section with, I just talked about ferromagnetism and ferroelectricity, and we went through different phenomena associated with both kinds of materials. One, there is ordering of magnetic moments. The other, there is spontaneous ordering of electric polarization, and there is always a mechanical force associated with both, either in a magnetic field, which is magnetostriction, or an electric field, which is the piezoelectric effect. And then we know how to put these two phases together to make it a magnetoelectric composite, and we know what to do with how to measure the overall magnetoelectric coupling by different means, either the effect of an external magnetic field or an electric field. Okay. Right. So, let me take any questions, then we will go on to the next topic.